So I work as part of the Credo team at Amazon AWS. Credo is Amazon's open source distribution of Java. So anyone that needs open source Java builds, we build those, we put the security patches in, we're very diligent in making sure that it's reliable and secure. We also focus on making it serve the needs of the Amazon AWS community more effectively. And that is one reason why we've been investing for a little over almost 3 years now in making the Shenandoah pauseless garbage collector more efficient. So garbage collection is one of those things that we hope to never have to think about. It's something that as a software developer, it should just happen and happen correctly for you. But I've spent over 30 years spending all my energy looking at garbage collection. So I'm going to share a little bit of that with you today and talk about why it's important to have a garbage collector that does the things you want it to do automatically. I'll give a little bit of a background on how garbage collection has evolved with Java over the years. Give some concepts so that you can understand what the Shenandoah garbage collector does and how that's different from some of the other garbage collectors, and then talk about how we add generational capabilities to the Java garbage collector and why that's important to you. If you look at the early history of Java garbage collection, it has evolved over the years. I think the initial garbage collector wasn't even generational. Within a couple of years after the initial release, we added a generational capability. The idea of a generational garbage collector is that we can focus our attention on recently allocated objects, because most of the recently allocated objects become garbage very quickly. The garbage collector's effort is proportional to the live data that has to be collected. So if we have a large region that's almost all garbage, that's very, very easy to garbage collect. And so that's where we focus attention with a generational garbage collector, where it's easy. A parallel garbage collector, and this is terminology introduced in the Java world. A parallel garbage collector uses multiple cores to do the garbage collection effort. So with multiple cores, you can get the garbage collection done more quickly. I added, as part of the history of Java garbage collection, some discussion of real-time garbage collectors. These actually evolved very quickly after the initial release of the standard Java. I was instrumental in the PERC Java, real-time Java virtual machine. But there are a number of these that emerged in the first few years after Java was released to the public. And the focus on a real-time garbage collector is being predictable and deterministic, but not necessarily fast. But this has been used in a variety of automation applications, including weapon systems. And it has evolved into the work we're doing now with Shenandoah pauseless garbage collection. About 2002, concurrent mark and sweep was introduced. Now, the idea of a concurrent garbage collector in the Java terminology is that the Java threads continue to run, your application continues to run at the same time the garbage collection is being performed. The concurrent mark and sweep is also generational. The older generation, that's the data that's been around for the longer period of time, that is the largest percentage of live data. So that's what we do concurrent marking on, because it takes a long time to concurrently mark large amounts of live data, and your application can continue to run while that's happening. One of the shortcomings of the concurrent mark and sweep, the CMS garbage collector, is that it did not defragment memory. Garbage was reclaimed, but it could be scattered throughout the heap, and this could create problems. And so CMS had a fallback mechanism that if the memory became too fragmented, it would stop the world, and I use STW to abbreviate that, and it would fully defragment the old gen memory. So more recently, the G1 garbage collector has replaced CMS in kind of relevance. And this introduces something called the garbage first heuristic. And the idea here is, besides generational, which focuses on the most recently allocated objects, the G1 garbage collector focuses in the older memory on regions that are mostly empty. And so that also improves the efficiency of garbage collection. It spends its effort where garbage collection is easiest, where you can get the most bang for your buck, the most usable memory with the least amount of effort. With G1GC, you do have stop the world phases for what they call a young gen collection is stop the world, and what they call mixed evacuation, and I'll talk a little more about that in a moment. And finally, we have pauseless garbage collection, and that's where I want to focus most of today's talk on. Shenandoah was introduced with JDK 12 around 2019, ZGC, JDK 15, 2020. These are when they were first available for production use. They actually began experimentation and development before these release dates. So, focusing today's talk on the generational enhancements to Shenandoah particularly, but Oracle is also working on generational enhancements to ZGC. So to describe how Shenandoah garbage collection works, it's very traditional in the phases of execution. So we begin with a mark phase, then we do evacuation of the live objects from the regions that are chosen to be collected. And then anything that's been moved, if there are pointers to that moved data, we have to update all those pointers. And so we call that the update references phase of garbage collection. So we find the live data, we relocate the live data to contiguous locations. That leaves a bunch of regions that have been evacuated. They are fully empty. We've reclaimed all that memory. Then we update the references to the pointers to the objects that have been moved. With Shenandoah garbage collection, almost all of the garbage collection work is concurrent. That means the application continues to run while the garbage collector is running. There are these brief moments of coordination, which are, they are pauses, but the pauses are generally with JDK 17 and beyond a millisecond or less. Before JDK 17, they were up to maybe 10 milliseconds typically. So if we look at, just briefly, comparison between the Shenandoah garbage collector and parallel garbage collection, the difference is that all of this is stop the world with parallel garbage collection. And so, whereas Shenandoah has a few pauses of maybe a few milliseconds at a time, parallel garbage collection can have multiple seconds of pause time. Similar behavior, though, in terms of what it does, just everything is stopped while it's happening. So there are typical comparisons made between parallel garbage collection and a concurrent garbage collector like Shenandoah. One observation is that because we've stopped the world, we don't have to coordinate between the application code and the garbage collector. If the application is modifying objects while the garbage collector is working on those objects, you have a synchronization issue. And that requires some, what they call barriers. Every time the mutator changes code, changes the object, it executes a barrier to leave some breadcrumbs so that the garbage collector can figure out what just happened to the reachability graph. On the other hand, so on the one hand, parallel runs faster because it doesn't need the barriers. On the other hand, Shenandoah can run more efficiently if you have large numbers of cores, because garbage collection is not so much benefited by caches. The garbage collector is very non-localized. It has to traverse the entire heap, and it does it in a random order. And the caches can't help garbage collection as much as they can help typical application code. So your garbage collection process is largely memory bound. If you have a very large server with, say, 96 cores on it, and they're all working in parallel on the single garbage collection effort, it's going to be memory constrained, memory bandwidth, memory bus constrained. And you're going to have a very low high cycles per instruction. So this is a benefit and a scalability strength of a concurrent garbage collector. The other point I want to make is that the concurrent garbage collection, while it does not itself benefit very much from the cache, it will impact the cache. So this is another possible downside. The concurrent garbage collection will make your application code perform slightly worse in terms of cache behavior while it's happening. G1 garbage collection uses a concurrent mark for the old gen. So this part of G1 garbage collection is very similar to the way Shenandoah works. But when G1 does its evacuation and updating, that is a stop the world pause. So that's a comparison. And this is why you have a max pause millis when you configure the G1 garbage collector, and the default behavior is 200 milliseconds. And what they're saying is, we're going to divide this work into small chunks, each of which can be completed in about 200 milliseconds of time. And so what you might find at the end of a G1 concurrent mark phase is that you've identified maybe 100 regions that you want to compact or collect, and the G1 garbage collector will follow the mark with multiple mixed evacuations. That means it will take some subset of the regions you want to collect, and it will collect those with a single atomic action, and then it will start it over again without doing another mark. It will preserve the mark information it already finished, and it will do another evacuation. So you see multiple mixed evacuations. To motivate this work, I want to describe some of the AWS services that have made the transition to Shenandoah from previous collectors. In this case, around September 2020, we had a service that was running with the G1 garbage collector. You probably can't read these, but these are just the different percentile rankings. So at P50, it was running about 60 millisecond latency. At P99.99, it was running around 230 millisecond latency. And after this service switched to Shenandoah, and this was with JDK 11, they got their P99s down to no more than about 40 milliseconds. And they got their P50s down to about 10 milliseconds. So we began seeing services move from G1 to Shenandoah in that time frame. Another service transitioned in September and got similar benefits. And finally, I have some slides that show the transition from JDK 11 to JDK 17. This is sticking with Shenandoah, but you see some noise here becomes much more refined. During an experiment with JDK 17, they had to roll back because they found some issues. They didn't migrate. I zoom in on the scale here and again. But this is where, with JDK 17, Shenandoah uses concurrent stack scanning. They call it root scanning, so it can traverse the content of the thread stacks without a long stop the world pause. And so our typical pause times came down from, say, 10 milliseconds to just 1 or 2 milliseconds. So always a benefit to moving to the latest and greatest technology. So I want to talk a little about some of the difficult challenges and trade-offs we face when we move from a stop-the-world garbage collector to a concurrent garbage collector. So first of all, a benefit, reduced GC pause time. On the other hand, we need a much larger memory buffer, and I'll motivate that claim in a moment. The other point I want to make is that with a stop-the-world garbage collector, the question of when do I perform garbage collection is much easier. The answer is, well, I do garbage collection when I run out of memory, okay? With a pauseless garbage collector, that is not acceptable, because if I wait until I'm out of memory, then even if I'm capable of doing concurrent execution, the application can't proceed because there's no memory for it to proceed with. So I have to start my garbage collection before, and that requires a guess as to when are we going to run out of memory. I want to give some motivation here with an illustration. So suppose we have a workload that has a 2 gigabyte live data set, and it's allocating at 10 gigabytes per second. Now you have to ask yourself, is that representative of my world or not? And I'll just say there are many Amazon services that is representative of. And that's a big part of the reason we were driven to do this work. So what happens if it's allocating 10 gigabytes per second? I am charting the in-use memory. So if I start here at time 0 and I run for 1 second, I'm going to allocate 10 gigabytes of memory. Now, all of that memory that gets allocated while garbage collection is running during this 1 second of concurrent time is much of it is garbage by the time we're done with this 1 second of execution. But because it was allocated during this collection cycle, it's live. As far as the garbage collector is concerned, it was live during this pass, so I can't reclaim it. Now, I continue to run, and it takes me a whole nother second to finish the next garbage collection pass. So by now, I've allocated 20 gigabytes of memory in 2 seconds. And it's not until now that I can reclaim the objects that were allocated and became garbage here. But I can't reclaim the objects that were just allocated here. So what happens, I get this saw blade shape that says I'm hovering between, say, 22 gigabytes and 12 gigabytes, even though my live memory usage is only 2 gigabytes of memory. So it's a very, using a concurrent garbage collector is quite memory intensive. This garbage that we can't reclaim immediately, we call it floating garbage. So I just motivated why this workload requires 22 gigabytes of memory. Now, what happens when you run a generational garbage collection is that the garbage collector has to do much less work because it only has to focus on the recently allocated data. And so we can, and this is hypothetical but realistic, we can do a generational garbage collection in a quarter of a second instead of a full second. And that means I can do 4 garbage collections in the time it used to take me to do 1 garbage collection. And the benefit ultimately is, if you do the same math that I just showed you, you can do this same workload in only 7 gigabytes of heap instead of the 22 gigabytes of heap. Now, at the scale that's typical of Amazon and probably many of your services, where a fleet is 10,000 or 30,000 nodes, this adds up to a huge cost in terms of capital expenditure, buying all those servers, but also operating costs to power all that memory and to cool those server farms. So, number one, we can achieve much smaller heap sizes, but we have other trade-offs that are equally valuable. We can, at the same memory utilization, we spend less CPU time, and or we have more flexibility as to when we do the garbage collections. Now, back at the same time, early 2020, when people were beginning to shift over to Shenandoah, we did some stress load testing. And we observed that under heavy stress, even though Shenandoah is designed to be a pauseless garbage collector, it wasn't delivering all of the benefits that our target customers were looking for. And so here on a heavy workload, we saw, for example, that the client response times delivered to our customers were much better with G1 than with Shenandoah, both in the average cases. This is G1 down here, and average for Shenandoah is up here, and in the maximum cases as well. And so the design wins that I showed you on the previous slides, those corresponded to lightly loaded systems in terms of the memory demand, the allocation rates, and the utilization. But if you put a heavy stress on Shenandoah, it did not deliver those kind of benefits. This workload is based on measurements. We call it Extremum, Extreme Memory Benchmark. We developed it ourselves. It drives pauseless garbage collectors. And there's a number of metrics it delivers. The one I'm measuring here is product replacement processing. I'm going to zoom in here. We're going to look at the 768 megabyte heap size. This is where memory utilization gets higher. This is where it's worst. We're going to look at why it's behaving poorly. But first, I need to explain a little bit about how Shenandoah works. So every time we start a garbage collection, it's a race. It's a race between the garbage collector and the application workload. The garbage collector says, I've got to reclaim memory and give it to the application as fast as I can. The application says, I'm not going to wait for the garbage collector. I'm just going to keep running as fast as I can, and that means I'm going to keep allocating memory. And so if the garbage collector loses the race, Shenandoah says, I failed, and it degenerates. And that means it goes into a stop the world mode. And this is what's happening under heavy workloads. So when Shenandoah is configured properly and it's working well, what you see is that this chart now is available memory, not the memory in use. So we start out with a lot of memory available, but the application keeps running, so it keeps allocating, so the available memory gets smaller. After we do the marking, we'll discover that certain objects, certain regions are entirely empty. We can immediately reclaim those regions, and so we replenish a little bit of memory into the available pool. This has not always happened. It sometimes happens. It's a bonus when it happens. Next, we continue to run concurrently. Sorry, I went too fast there. We continue to run, and memory continues to be depleted. At this point, everything that was evacuated, all those regions now get thrown into the allocation pool, and we've significantly replenished the free pool. What I'm showing now is what happens when we lose the race. So if we started the garbage collection too late, we run out of memory before it's been replenished. We lost the race, and we do a degenerated mode. And this is a long period of time that the application cannot run. And what I want to emphasize, and I don't know if you can see it, but the slope of the available memory line trend is lower here than here. What happened is, because we paused our service while the garbage collection was performed, we are now way behind on our assigned work. So the queues continue to accumulate requests, and all of a sudden I have to play catch up. And so now I have to allocate even faster than I had before. So that's one of the points I want to emphasize about how a pause impacts your workload. So if we want to analyze this and represent it with metrics, we say this is a very long pause during our execution. And on the next chart that you're about to see, we distinguish the pause times from the concurrent garbage collection times with pauses. And in the ideal, we have lots of concurrent GC times and no pauses. So just to summarize what we see in this example, we're spending about 50% of our total execution time in concurrent GC with pauses, and about 35% of our time totally paused. So out of every second of execution time, I'm spending 350 milliseconds paused, for example. Now, go back to that chart I showed you. When we zoom in on that 768 megabyte heap configuration, we see that once we start the experimental workload, which starts about here, we start seeing a whole bunch of long pause times. This is the degenerated behavior, and it's 1 in 10 garbage collection passes was degenerated. We were just unable to win the races. And that is why the response latency seen by the clients using Shenandoah garbage collection under a heavy load is actually worse than with G1 GC. We did extensive studies. What we concluded was Shenandoah GC works very well if you have low allocation rates, even if you have a high memory utilization. And it works very well if you have high allocation rates, but you have a low memory utilization. So in the generational mode of Shenandoah, our goal was to exploit both of those strengths. Number one, notice that young generation, very high allocation rate. That's where you're getting 10 gigabytes per second. But at the end of the cycle, it's almost all garbage, very low utilization. The old generation has a very low allocation rate. The old generation just takes the few objects that survive young gen collections and promotes them. Very low promotion rate generally. But your goal is to have a high memory utilization of old gen memory. This is stuff that stays around and persists, your caches, your databases, and so forth. And you could conceivably achieve 85, 90% utilization in the old gen. The way we see it, young gen allocations are very critical. They're happening at a high rate. So we run the young gen collections at a very high priority and a high frequency. The old gen happens much more rarely and does not need to run at a high priority. It can actually be preempted by the higher priority young gen collections. What we typically see is that we can complete tens or even hundreds of young gen collections in the time that we need to do one old gen collection. So the way we structure our solution is that when it's time to start an old gen collection, we, I'll say, piggyback on one of those very frequent young gen collections. Every time we do a young gen collection, we have to start by scanning the roots. The roots are the stacks of all the running threads, for example. So when we're going to start a old gen, we call it a bootstrap collection. And we just say, okay, every object in here normally, if it points to old gen, the collector ignores it. But now we say, if it points to old gen, tell me about it, because I actually care. I'm going to start looking at old gen memory. After we're done with the old gen collection, we're going to piggyback again. Every young gen collection has to, it does its marking to find the live data, and then it does evacuation. Now we're going to say, besides evacuating young objects, I'd like you to evacuate some old regions as well. So we piggyback the old garbage collection effort on those very frequent young gen collections as well. And this is what it looks like. When you're running, the service threads continue without interruption. We do an increment of old gen collection. It's a big effort, lots of old gen memory, so we don't do it all at once. When the young gen says, hey, I'm about to run out of memory, it preempts the old gen and it does a young gen collection. Then it finishes, it's replenished the young pool, and the old gen concurrent marking resumes. And on we go. At some point, the old gen effort finishes. It's completely marked all of the old gen memory. That was, maybe 2 gigs, maybe 20 gigs of live data. It's finished marking what's live. At this point, the old gen says, I've got a desire to evacuate n regions of old gen memory, compact those regions. And so now we begin what we call mixed garbage collection passes. The young gen, on the subsequent garbage collections, he's going to say, well, I'll collect all of my young memory, but I'll also carry some of your burden, and I'll collect some subset of all the old gen regions that you want to collect. And the number of those depends on the number of young mixed passes, depends on how much old gen memory we want to defragment. After we've collected all of the old gen memory, we go back to the other mode of operation where it's just young gen by itself, and eventually young gen preempting old gen marking. Remember that G1 has this garbage first heuristic, says I'm only going to reclaim the regions that are highly low utilized or high garbage collection content, because those are the easy regions to collect. Shenandoah and generational Shenandoah do the same thing. When we choose a collection set, we choose regions that have low memory utilization, high percentage of garbage. That allows us to operate more efficiently. With both G1 and Shenandoah, following an old gen mark, you get multiple mixed evacuation passes. The objective in G1 of limiting the size of each mixed evacuation is to honor the max GC pause millis specification that you gave it. You said, I want you to pause no longer than 400 milliseconds or 100 milliseconds. And so it limits how much it tries to evacuate in its mixed evacuations to honor that request. With Shenandoah, we do the same thing. We limit the size of the mixed evacuations, but not so much to honor max GC pause millis, but more because we want to make sure we do not disrupt the cadence of young gen collections. The young gen collector has to run maybe every quarter second in order to replenish the allocation pool for the service that says I have an insatiable demand for memory. If we try to do all of the old gen evacuation in a single mixed evacuation, that would cause the young gen to take too long, and we would exhaust our free pool. Remember that with G1, the young collection is stop the world. The size is constrained by the maximum pause time, and it's triggered after you are out of memory. With Shenandoah young garbage collection, we have to anticipate when we're going to run out of memory. So we trigger the start of that before we run out, but it's concurrent, so there's no long pause associated with a young collection. With Shenandoah, well, let me go back with G1, the young collection evacuates everything that's in young memory. With Shenandoah, we actually apply the garbage collection, the G1 heuristic, the garbage first heuristic. So G1 with Shenandoah, we only collect the young memory that is highly garbage. Both G1 and Shenandoah have the notion of Eden, where we can allocate very efficiently, and survivor spaces, which accumulate young objects of intermediate age that have not yet become old enough for promotion. I'm going to show some charts showing our incremental progress with generational Shenandoah. This first chart is showing an allocation rate of 67 megabytes per second and 1 gigabyte of live memory. The generational is the red stars. So it's kind of right in the middle of the pack here. And this is a P50 number. So this is kind of like typical of a client response time. Some interesting observations that you would normally expect: the larger the heap size, the better the efficiency of the garbage collector. And you see some of these kind of slope downward towards the right, but G1 and ZGC do not so much. And that's partly, let me just say about G1, it's intentionally lazy, and it's trying to use all the memory available. And so it basically behaves more or less the same, regardless of how large the heap is. Here you see that trend also. Towards the right, it gets smaller. This is at P99.99. Here you see the big divergence between parallel G1 up here with latencies in the 50 to 60 millisecond range. And you see the pauseless garbage collectors all hover down here. And what's kind of nice is the generational Shenandoah is actually showing its strengths as you get to the higher memory utilization, the smaller heap sizes. And this was at P100. Similar kind of behavior, but generational Shenandoah even more noteworthy in its strengths over the other garbage collectors. I did another study a few months later, and here we're looking at a 444 megabyte per second allocation rate. And at P50, once again, generational Shenandoah, not so special, but close to the pack. And then as you move to higher latencies, higher percentiles, then you see that generational Shenandoah begins to distinguish itself and show its strengths over other garbage collectors. And finally, I wanted to show, one other chart here. This is a almost 2 gigabyte per second allocation rate with a 6 gigabyte heap, 38% live. And what's really nice here is to see that generational Shenandoah, when it's been hand-tuned, significantly better than all the other technologies in P99.9 and 99.99. We still have a hiccup here we're not happy with, but I want to emphasize this shows the strengths and the potential of generational Shenandoah. We consider that we have significant work still to be done. In particular, hand tuning, something we can do in the lab with a lot of blood, sweat, and tears, but doesn't work so well for our typical customers. And so we're automating all those tuning parameters, and I'll talk about that in a moment. Also very unhappy with this number. There are still some degenerated behaviors occurring, and there's the need for us to adapt the tuning on the fly as we discover the way the application is working and behaving. And we're also aware of some performance bottlenecks where our generational Shenandoah is not as efficient, for example, as G1 GC in representing the pointers from old gen to young gen and remembering what has to be addressed every time we do a young gen collection with regards to those pointers, the intergenerational pointers. So we're working on all of those areas as we speak. So one question you might ask yourself, is this ready for production use? Not quite yet. We have some services inside Amazon that are starting to experiment with it in very limited circumstances. But it needs some work before we recommend it for production use. We're also, the second reason why it's not recommended for production use, besides some of the technology, we're not in a DevOps mode of operation yet, where if you have an issue, we'll jump on it and promise to solve it overnight. We're just still focused on performance issues that might take weeks of time. But I will say that we are automating our build and release process for the experimental versions of generational Shenandoah, and we are integrating security patches automatically and testing automatically, so that should happen within a few months, that you would be able to put some of this technology into experimental pipelines if you might be interested in doing so. As I mentioned, I'm part of the Credo team. Generational Shenandoah is not available in Credo yet, but we are providing experimental builds of Credo JDK 17. So it's not the standard Credo distribution, but you can follow a link. I'll give you that link in my slides, and you can experiment with that experimental build. As I've shown you with some of these statistics, we do see the benefits on real workloads and on a variety of experimental workloads. We're focusing on automatically and tuning and adapting the configuration. We're making adjustments to the way we schedule when to start the garbage collectors to make it both more reliable and more efficient. And then we're addressing scalability issues. We are working to get this integrated into OpenJDK. There is a JEP that describes our efforts, and we will very soon begin the process. All of the source code is in the upstream community, but it's not integrated with OpenJDK yet. It's on the Shenandoah project, which is hosted by GitHub. We'll be merging it into standard OpenJDK distribution soon. So some might wonder, what do I mean when I say you have to do manual tuning of generational Shenandoah? You have to specify the heap size. You have to specify how big you want the young gen and how big you want the old gen. This is a static configuration right now. It is being adapted. There's development work right now. Will be integrated within a couple of weeks to automatically size and adjust the sizes. The tenuring age. So by default, if an object survives 7 young collections, it will be promoted to old. That's not the right answer for every service. So you have to set that right now. That's also being adjusted automatically. Within a matter of weeks. I think that will be integrated as well into the release. The number of concurrent GC threads. So if you have 16 cores, the default configuration might be 4 GC threads, but you might choose to increase or decrease those default numbers. That's also something we're going to automatically adjust. You can specify a threshold that says, if old gen gets to be 90% utilized, trigger an old gen collection. Those have default values, and that's a secondary threshold because our preference is that we schedule based on our prediction of your service has a certain allocation rate. We can measure that, we observe that, and we know how long it takes in wall clock time to complete the garbage collection. So we use that as our primary choice for when to trigger garbage collection. But if you want to put a secondary safeguard in and say, by the way, if you think you can keep going, but you're this close to the edge, start the garbage collection now. So you can put that parameter in place and say, don't let it get less than 15% available, for example. Those are the key kind of parameters that need to be adjusted, and we're working to automate those adjustments. Where does this play? You know, I say we can promise you maximum pause times of a couple milliseconds, but anytime your service has a response time goal that's below 100 milliseconds, then you might want to look at something like a pauseless garbage collector, particularly Shenandoah, generational mode. Now, if your service does not have a combination of long-lived data and short-lived data, then there's not a lot of strength or benefit from a generational mode. But a lot of services do have persistent data in combination with a lot of transactional data that goes away very quickly. And that's the kind of workload that works well with generational mode. And finally, if you care about efficient use of memory, CPU cores, electricity for powering your equipment and cooling your servers, that's where this technology is relevant. There's a suggestion that if you want to experiment, and we'd encourage you to do so, we very much value the feedback we get from actual customers. That's what's guiding our priorities right now in terms of what we're doing to make it better. Open a ticket, explain what you're trying to accomplish, why you care about it, and what you observe when you experiment with it. And we'll work with you to help you configure it, and we'll work with you to make it work better for you. This is where you can download the builds from. And I'd encourage you to do so if you might be interested in using this technology. This says I have a couple minutes for questions. If there are any, I'd be glad to take those now. I don't know if we really have a couple minutes or if we're kind of behind schedule already. What? No questions? Okay. Yeah, good. Thank you very much. I will watch the Discord channel.